throughout our discussion of the mathematical structure of quantum mechanics, I've been writing down things like psi, the vertical bar on the left and an angle bracket on the right. This is the notation that we've been using for vectors in the Hilbert space, the infinite dimensional vector space where quantum mechanical states can be easily represented. I've also been writing things like alpha, beta with angle brackets on either side and a vertical bar in the middle, representing inner products between two vectors in that Hilbert space. Now, this notation with angle brackets and vertical bars is due to Paul Dirac. It's properly known as Dirac Notation, and it turns out this notation is actually more useful than what we've been using it for so far. It can actually concisely express a lot of the key ideas in quantum mechanics. So let's look at this notation in more detail and see how far we can get with it. The fundamental problem in quantum mechanics is determining the state of a quantum mechanical system. This psi, living in a Hilbert space, is not something that we can ever actually hope to write down. So we have a couple of different representations that we've been using. First of all, we started with the wave function, psi of x, representing, for instance, the sort of square root of the probability density for position measurements. We also talked about phi of p, the momentum space wave function, and we talked about representing, say, states of systems as superpositions of stationary states. So, for instance, if I have a particle in a box, I have some set of wave functions that have coefficients, various coefficients multiplied by them. I can superpose them together to reconstruct any physical state. And these representations, either as a wave function in momentum space, or a set of coefficients in the context of a particular set of functions, are all mathematically equivalent representations. I can go from one to the other and back. The superposition of stationary states can be easily used to construct, for instance, psi of x as a sum over n of c sub n, psi sub n of x. These are the stationary state solutions. I'm multiplying them all by a coefficient, and I'm superposing them all together to give me my overall wave function. That's going from this representation to this representation. We can also go, for instance, from in between these two sorts of representations. You can think of psi of x as being given by an integral from minus infinity to infinity of phi of p e to the I p x over h bar divided by root 2 pi h bar, the integral dp here, this takes this coefficient phi of p and multiplies it by a state with known momentum, and then we're superposing a whole bunch more states of known momentum to give me the overall state that I'm interested in. You can also go back, finding phi of p from psi of x. For instance, phi of p is going to be equal to the integral from minus infinity to infinity of, let's see, e to the minus, there's my eraser, e to the minus I p x over h bar divided by root 2 pi h bar, multiplied by psi of x, and this is going to be an integral dx. So given these various representations, I can convert from one to the other. If I had the general quantum mechanical state, I could go from it to any of these representations fairly easily. We talked about C sub n, for instance, which could be computed as an inner product between the state psi sub n and the general state that you're interested in, psi. This is a very compact notation for an integral of some arbitrary function of x multiplied by some other function of x, if you have the position function representation of these states. If you don't, you can use this Dirac notation to express the idea of that inner product. Essentially, this is computing the component of psi in the psi sub n direction. That's what these vector products sort of do. Likewise, you can think of phi of p in the same sort of way. Phi of p can be written as the inner product of p and that arbitrary wave function that I'm interested in representing. What this represents, this p here represents a wave function or a state of a quantum mechanical system with known momentum p, essentially an eigenstate of the momentum operator with eigenvalue p. So I'm sort of using p here, the eigenvalue, to index the eigenstate with that appropriate eigenvalue. This has the same sort of feel to it as this sort of expression. I have some function of known energy, and I'm using it to pull out a coefficient that is appropriate for superposing a bunch of those functions together. Here I'm using a function of known momentum to compute an inner product, which gives me a coefficient, which is appropriate for, say, reconstructing wave functions by superposing a bunch of functions of known momentum. Likewise, I can even write psi of x in this notation, and it's going to look a little silly, x inner product with psi, where this x now represents a quantum mechanical state of known position. Now, it's a little bit silly to think about this, but just as an example, we can write down psi of x, this representation for an inner product. I'm going to need some function that represents a quantum mechanical system with known position. Well, that's easy. It's a delta function that only has support as a function of some other variable where that variable is equal to x. So I'm going to be integrating minus infinity to infinity of some dummy variable xi here, and I'm going to be multiplying it by psi of xi. Now this is a silly expression. If I have psi of xi, why would I bother constructing an integral of it just to get psi of x back? Why wouldn't I just plug x into psi of xi? There's no reason to, but it highlights the mathematical similarity of these sorts of coefficients. Psi of x can be thought of as an inner product between a delta function and the wave function, or it can be thought of as an inner product between a quantum mechanical state that only has position x and no other positions, and the general state that you're interested in. So these sort of expressions here, this is obviously a very compact and versatile notation. It's capturing the idea of coefficient in sort of a discrete basis, a momentum basis, or a position basis, functions of position, functions of momentum, or functions of energy in this case, C sub n's being solutions to the time-independent Schrodinger equation, or the coefficients that multiply them out front. So this notation is concise, it's clear, it captures the notion of pulling out a particular component of some general state to compute a coefficient to represent that state in a particular sort of basis, position, momentum, or stationary state wave functions for the particle in a box. That's really what we care about, is this sort of abstract notation. We have psi, that's our state, and we can use psi to compute a whole variety of representations. I can use it to compute psi of x, phi of p, or any set of coefficients with respect to any set of stationary state wave functions. So these representations are going to be numerous, but there's really only ever going to be one state. And the state determines the representations, not the other way around. So instead of thinking about the state of the system as being as psi of x, think of psi of x as a representation of a more broad mathematical object that can be used to construct other representations, can be used on its own to express quantum mechanical ideas. It's actually a very powerful notation. Now, beyond just representing states in quantum mechanics, we'd also like to be able to represent operators. So what do operators look like? Well, the general operator that I've been working with is something like q hat. Probably it's a Hermitian operator. It represents an observable. In general, operators act on vectors. Let's say an operator acting on some vector alpha will give me another vector. These are linear transformations. So there's a lot of linear algebra that can be used to work out how linear operators behave. Now, if I'm representing states in a variety of bases, I ought to also be able to represent operators in a variety of bases. And let's work out what that representation might look like. Suppose I have some vector alpha represented as a superposition of stationary states for the particle in a box. So I have some set of coefficients a sub n in terms of psi sub n, where, as before, these a sub n's are computed by inner products with my overall wave function, which I should probably write as alpha here. So, very circular definition. Probably I have the a sub n's without having to independently calculate them, or I have some meaningful representation of a sub n that I'm converting into this set of a sub n numbers sort of representation. Likewise, I can do the same sort of thing for beta. Beta is going to be a sum. Also, let's say sum over n, b sub n, psi sub n, computing betas in the same sort of way. Now we can plug these sorts of representations into this expression, figure out how that sort of expression behaves. I'll have q hat applied to a sum over n of a sub n, psi sub n, and that has to be equal to sum over n, b sub n, psi sub n. Now, this means I've got an infinite sum on the left and an infinite sum on the right, but these infinite sums, you know how to make them disappear. We multiply through by, or we take an inner product with a particular psi sub m and use the orthogonality properties of these psi sub n's to figure out what the result will be. So if I do that, well, let's see. First, let me distribute this operator in. So I'll have sum over n of a sub n q hat acting on psi sub n, and that has to be equal to the sum over n of b sub n times psi sub n. If I take both the left and right sides of this equation and make an inner product with, say, psi sub m, distributing this psi sub m inner product into both sums on the left and the right, then on the right-hand side here, I will end up with a lot of expressions that look like this. This is going to be a sum over n of b sub n, and then I'll have psi sub m, psi sub n, distributing the psi sub m in. This is going to be a Kronecker delta. If this is a complete orthonormal set of basis functions, which we are going to get if we're working with, say, particle in a box stationary states. So this sum is only ever going to be, these terms in the sum are only ever going to be non-zero when n equals m, which means this right-hand side here is just going to become b sub m. The left-hand side, though, there's really not much that I can do with. All I've got is a sum over n of a sub n, psi sub m, q hat, psi sub n. Now, the beauty of this sort of notation is that you can think about b sub m. This is the representation for the result of the operator acting on the vector a, right? If I plug in a different value for m in these sorts of expressions, I'll get a different value for b. I can write that as the sum over n of a sub n times something that's really just a number. It's the result of, psi sub m, q hat, psi sub n. So if I have my psi sub n's, some complete set to work with, I can compute all of these quantities just by plugging in, say, m equals 2 and n equals 3, m equals 5 and n equals 1, etc. It's going to depend only on m and n. So we'll usually write this as some number q sub mn. It has two free indices. This is a matrix. It's a table of numbers. In this case, it's an infinity by infinity matrix, but it can still be thought of as a matrix. And it turns out that a sum like this, summing over n, where if you're thinking about this as a matrix, row index, column index, this is summing over columns of this guy and lining it up with elements in a sub n, where I have a whole set of a sub n's. You can think about this guy as a vector, and this whole thing is a matrix vector product. That is a very, very useful approach to representing these things. Instead of having to think about arbitrary quantum mechanical states in an infinite dimensional Hilbert space, you can think about matrices and vectors. And there is a massive machinery, computationally speaking, for working with matrices and vectors. You can compute eigenvalues, you can compute eigenvectors, you can do expansions, you can do change of bases. There are all sorts of things that you can do with matrices and vectors that are going to be now immensely useful to quantum mechanics, thanks to this representation of general operators expressed in a particular basis as matrices. So that is immensely useful. We can go a little further down the rabbit hole, though. To up the generality of this overall thing, there is actually a mathematical structure. If you're thinking about something like the state psi as represented in the Hilbert space, this I described earlier is read as bra-psi, whereas this is ket-psi, whereas this is read as bra-psi. And these things actually represent different mathematical entities. If you're thinking about ket-psi in terms of wave functions, this is psi of x. If you're thinking about bra-psi in terms of wave functions, it's psi star of x. It doesn't seem like there's anything terribly different about those two things, but really it is a mathematically distinct concept. Bras and kets, angle brackets on the right versus angle brackets on the left, are really only ever going to come together in something like an inner product, something like alpha, beta. And as such, this alpha on the left doesn't itself have all that much quantum mechanical meaning. Bras, in this case, are actually elements of a mathematically distinct space called the dual space. It's a vector space that obeys slightly different rules than the vector space of psi, of kets, excuse me. And really what happens is when you combine something from the dual space with something from the space itself, you end up with a number. So these inner products are always going to be numbers. As such, excuse me. As such, the wave function psi and the wave function psi star is actually a different beast. It's not so much psi star as it is psi star integrated and multiplied by something else, integrated to dx. So bra psi really represents this mathematical entity. It's something that when I slot in a ket gives me a result, a number, right? This is going to give me a number as well. So we have this notion of one space and another space as defined in the dual context. Now within the notion that we just talked about, where when I'm expressing some vector psi in a basis, then psi itself becomes a set of c sub n's, right? I can compute psi n psi, and that gives me c sub n. That set can be thought of as a vector, and within the mathematical structure of the space and the dual space, I have to say c sub n is a column vector. This set of c's, c1, c2, c3, c4, etc. The dual space, then, is something that when multiplied by a column vector gives you a number, and expressing bra psi in a basis then gives me something not so much a column vector as a row vector. Such that if I write down some sort of an inner product like this, I have a row vector representing bra psi, or bra alpha in that case, with a column vector representing ket beta, and these sorts of things just multiply together just fine to give you a number as you want. The one detail I've forgotten here is if you're going from a row vector to a column vector, as you can go from, say, a ket to a bra, you have to take the complex conjugate. So this sort of complex conjugate transpose thing is going to show up quite a lot when we're talking about matrices in the language of quantum mechanics. If you're talking about matrices, it's a Hermitian conjugate of those operators, and that's another element of the mathematical structure that we're working with here. So we have our wave function, we have our dual wave function in some sense, we have our row vectors, we have our column vectors, meaning our kets and our bras, we have our inner products. That's a lot of the mathematical structure that we're working with. And, working within the notation, or the ket and bra notation, is actually a very concise way of expressing many, many things here. You're not just talking about going from the wave function to its complex conjugate integral. You're working with row vectors and column vectors and row vectors complex conjugate, for instance. You can work with Hermitian conjugates in the language of matrices that are representing operators. It's a very concise notation. Once again, expressing a lot of the key ideas here. The difference between psi and psi star is a little bit more nuanced than just taking a complex conjugate. Another idea that we can express concisely in the language of the Dirac notation is orthonormality and completeness. If I have some sort of a basis, say, that I got by solving the time-independent Schrodinger equation for, say, a particle in a box for the quantum harmonic oscillator, orthonormality is easy to express. I've got some, say, psi n, some, say, psi m. Inner product is going to be expressed as a Kronecker delta. That's all there is to it. If I have a continuous set of basis functions, psi n, psi m isn't going to give me a Kronecker delta. I shouldn't if I have a continuous basis, I can't write it as psi n, psi m. I have to write it as psi p1 and psi p2. These continuously variable parameters p1 and p2 mean that psi1 or psi p1 and psi p2 are not going to be normalizable, and the result is not going to be a simple Kronecker delta. It's going to be more of a Dirac delta function, say p1 minus p2. Given this notion of orthonormality and orthonormality, we can talk about the completeness of a set of functions. We can talk about that completeness quite easily. Usually, the way this is done is to define something called a projection operator, usually written something like p hat sub n, and this is a definition. It looks in Dirac notation something like psi sub n, psi sub n. And this looks a little bit strange. Isn't this an inner product? Well, yeah, you could think about it that way, but if it were an inner product, it would just be equal to 1, because it's a normalization. But since I've got the bra on the right and the ket on the left, things are a little bit out of order. If you were thinking about these as matrices, this is going to be a column vector. This is going to be a row matrix. And those are not going to multiply the same way as a row matrix and a column matrix would. You're going to get some different results. This is actually an operator that takes quantum mechanical wave functions, or quantum mechanical states in the Hilbert space, from one to the other, the same way any other quantum mechanical operator would. It's not going to give you just straight away a number. You can think about applying this, for instance, say, sorry, I shouldn't draw it as a lowercase p, got to distinguish it from the momentum operator. Let's apply it to that state beta that I wrote down earlier. That's going to be psi sub n beta, inner product. This is an inner product, and this, if you recognize it, this is just going to be b sub n, the coefficient in the expansion, the representation of the state beta in the basis of psi sub n's. So this is going to then give you b sub n psi sub n. It's going to give you the portion of that expansion that's relevant to psi sub n. So if you think about summing up a whole bunch of different projection operators, this here would be p sub n, writing down something like sum over n of p sub n, if I applied that to some sort of beta here, I would get the sum over n of psi sub n times that b sub n. I would get this overall whole expansion back. This is just my representation for beta in this basis. So looking at this expression, this thing multiplied by beta did nothing. It just gave me beta back, which means this whole thing must in some sense be 1. So while we can express orthogonality in terms of inner products quite simply, we can also express completeness quite simply. If this is possible, if the sum of projection operators, sorry, I should write these with hats, gives me, in some sense, the identity transformation, taking a vector just to itself, then we have a complete set. So these are expressions for orthogonality. We can say completeness is expressed, say, as the sum over n of psi sub n ket psi sub n bra is equal to 1 in some sense. Now this 1 thing is not so much the number 1 as it is the identity transformation, since it's actually coming from this sort of complicated sum of infinite states in both spaces. But regardless, it's a very concise definition, or a very concise notation for the completeness of a system. So if you're good on mathematical notation, you've probably had your fill by now. Dirac notation is a very concise way of describing a lot of the core ideas of quantum mechanics. We've been spending quite a bit of time lately talking about solving the time-independent Schrödinger equation, representing arbitrary quantum mechanical systems as superpositions of stationary states. We can only do that thanks to the completeness of those stationary states and thanks to their orthonormality. We can find their components very easily, just by writing out, for instance, this beta sub n. B sub n is just psi sub n and that arbitrary state. So we've got our expansion coefficients, our representations. We've got all sorts of good things that we can do with this notation. Now, just to close, let me give you an example of how these sorts of things work out in sort of a two-state system. Now, two states obviously is not going to be a complete basis for an arbitrary quantum mechanical system, but oftentimes it's quite useful to think just along those lines. So say I have a set of two states, which I'll just write as state 1 and state 2. Let's assume again that these things are orthonormal. So I have that 1 inner product with 2 is equal to 2 inner product with 1 is equal to 0, and that 1 inner product with 1 is equal to 2 inner product with 2 is equal to 1. We can then express these general state vectors in their own basis. So let's say I want to represent the vector 1 as a sum. So this is kind of a stupid sum. I is going to go from 1 to 2 of these states. Let's call each one psi sub I, where this is either psi 1 or psi 2. Actually, no, let's not call it that. Let's just write it out as I. And you're supposed to know this is not the complex number. This is just going to be an integer, 1 or 2, multiplied by some coefficient. Now the coefficient here, we said a sub I was equal to I, inner product with the state in question. So in this case, my state is 1. So if I is equal to 0, if I is equal to 1, this is going to be 1. If I is equal to 2, this is going to be 0. So my representation for this state, no surprises here, is just 1 is equal to 1 times the state 1 plus 0 times the state 2. Now it's this 1 and 0 that I'm interested in, and expressing this in a basis is kind of silly to use the vectors in its own definition. So really, let's write this as the column vector 1, 0. It's a set of two numbers. We're keeping things in order of state 1, state 2. So state 1's contribution to state 1 is 1. State 2's contribution to state 1 is 0. No surprises there. Likewise, we can express state 2 in this language, and it's going to end up very similarly, except it's going to end up being the vector 0, 1. State 1's contribution to state 2 is 0. State 2's contribution to state 2 is 1. So this is in some sense trivial. I've expressed the basis vectors for a two-state space in terms of those basis vectors. Now, that's a process you should keep in the back of your mind if you're thinking about representing quantum mechanical systems. The basis vectors are always going to be simple in their own basis. Now, that's not always going to be the case. If I have some general quantum mechanical state, psi, probably it's going to be represented by, I don't know, alpha and beta, two different, potentially complex contributions. If I've got, for instance, the Hamiltonian operator, that itself is also going to be representable as a matrix. And we talked about those matrix elements. If I write them out as a 2 by 2 matrix, it's going to look something like 1 times h hat acting on state 1. And down here I'll have 2 acting on inner product with h acting on state 1. Here I'll have 1 inner product with h acting on state 2. And here I'll have 2 inner product with h acting on state 2. So if these two states themselves are eigenvalues of the Hamiltonian, then h times 1 is going to give you something, h times 2 is going to give you, well, h times 1 is going to give you something times 1, h times 2 is going to give you something times 2. So these off-diagonal elements here are going to be pretty easy to figure out. You're going to involve inner products of 1 and 2, whereas the on-diagonal elements are going to involve inner products of 1 and 1, or 2 and 2. So you can write down the matrix elements of a general Hamiltonian. Now, probably it's not going to be so easy. The Hamiltonian itself is really easy to write down in a basis of its eigenstates because of that sort of inner product structure that I just outlined. But in general, you're going to have some sort of a general operator, which in this two-state space is going to be some sort of 2 by 2 matrix. And now we have all of the tools of linear algebra to deal with our quantum mechanical states, either in their representation in this basis or, by proxy, in the general Hilbert space. We can do a change of basis, we can do expansions, we can do decompositions, we can solve systems of equations, we can do all sorts of things with linear algebra that we wouldn't have been able to do otherwise. So this is a very elegant notation. It's good at expressing the sort of general ideas, and it's even better if you're thinking about trying to construct specific representations of systems that wouldn't necessarily be representable in terms of wave functions. So we've sort of raised the bar for generality. We're not just talking about functions of position anymore. We're talking about general quantum mechanical states and systems of states. For example, the two-state system here. You can do a lot with this sort of notation. To check your understanding, let's consider a set of solutions to the time-independent Schrödinger equation for the quantum harmonic oscillator, these sort of psi sub n's. Let's first work out some matrix elements, both for the Hamiltonian operator and for A+, the raising operator. And you should know enough about the Hamiltonian operator and how it acts on stationary states, and the raising operator and how it acts on those same stationary states to figure out what the matrix elements ought to be. And both of these matrices, for the Hamiltonian and for A+, are going to have a fair bit of mathematical structure. So think about that mathematical structure and describe the matrix. It might help to sketch out where those matrix elements are non-zero, for example. But I think that's all that we'll be doing with Dirac notation for now. We'll come back to this much more later on in the course. For now, just know that Dirac notation is this notion of bras and kets, and the wave function and the state and all of its representations. Fairly easily. We talked about C sub n, for instance, which could be computed as an inner product between the state psi sub n and the general state that you're interested in, psi. This is a very compact notation for an integral of some arbitrary function of x multiplied by some other function of x, if you have the position function representation of these states. If you don't, you can use this Dirac notation to express the idea of that inner product. Essentially, this is computing the component of psi in the psi sub n direction. That's what these vector products sort of do. Likewise, you can think of phi of p in the same sort of way. Phi of p can be written as the inner product of p and that arbitrary wave function that I'm interested in representing. What this space, or a set of coefficients in the context of a particular set of functions, are all mathematically equivalent representations. I can go from one to the other and back. The superposition of stationary states can be easily used to construct, for instance, psi of x as a sum over n of c sub n, psi sub n of x. These are the stationary state solutions. I'm multiplying them all by a coefficient, and I'm superposing them all together to give me my overall wave function. That's going from this representation to this representation. We can also go, for instance, from in between these two sorts of representations. You can think of psi of x as being given by an integral from minus infinity to infinity of phi of p e to the I p x over h bar divided by root 2 pi h bar, the integral dp here, this takes this coefficient phi of p and multiplies it by a state with known momentum, and then we're superposing a whole bunch more states of known momentum to give me the overall state that I'm interested in. You can also go back, finding phi of p from psi of x. For instance, phi of p is going to be equal to the integral from minus infinity to infinity of, let's see, e to the minus, there's my eraser, e to the minus I p x over h bar divided by root 2 pi h bar, multiplied by psi of x, and this is going to be an integral dx. So given these various representations, I can convert from one to the other. If I had the general quantum mechanical state, I could go from it to any of these representations. Throughout our discussion of the mathematical structure of quantum mechanics, I've been writing down things like psi, the vertical bar on the left and an angle bracket on the right. This is the notation that we've been using for vectors in the Hilbert space, the infinite dimensional vector space where quantum mechanical states can be easily represented. I've also been writing things like alpha, beta with angle brackets on either side and a vertical bar in the middle, representing inner products between two vectors in that Hilbert space. Now, this notation with angle brackets and vertical bars is due to Paul Dirac. It's properly known as Dirac notation, and it turns out this notation is actually more useful than what we've been using it for so far. It can actually concisely express a lot of the key ideas in quantum mechanics. So let's look at this notation in more detail and see how far we can get with it. The fundamental problem in quantum mechanics is determining the state of a quantum mechanical system. This psi, living in a Hilbert space, is not something that we can ever actually hope to write down. So we have a couple of different representations that we've been using. First of all, we started with the wave function, psi of x, representing, for instance, the sort of square root of the probability density for position measurements. We also talked about phi of p, the momentum space wave function, and we talked about representing, say, states of systems as superpositions of stationary states. So, for instance, if I have a particle in a box, I have some set of wave functions that have coefficients, various coefficients multiplied by them. I can superpose them together to reconstruct any physical state. Now, these representations, either as a wave function in momentum